Today, we are going to explore the fascinating world of an electrical power system. Let's start with a simple question. What is an electrical power system and why it is important? Okay, now close your eyes and think about a day without electricity. Okay, imagine waking up in the morning and there's no lights, there's no power, there's no fan or air conditioner, and you cannot use the water heater. So how would your day start differently? Can you imagine it? So this activity highlighted the role of an electricity in our daily routine, from turning on the lights to charging our device. Okay, but have you ever wondered how electricity is produced and brought to us? This is where the power system comes into play. It's the behind the scenes force that ensures electricity flows from its source to our homes, schools, or industries. So this is the outline for this topic. Okay, so we will start with an introduction first, followed by the power system components, and then single line diagram per unit system, and finally power factor. So as an introduction, electrical energy is a form of energy that results from the movement of electric charges known as electrons through conductors like wires. It plays a crucial role in powering everything from our homes and workplace to transportation, communication, and industrial process. And power system actually refers to the network of interconnected components designed to generate, transmit, distribute, and deliver electrical energy from power generation sources to end users. And it is a complex and integrated infrastructure that enables the efficient and reliable supply of electricity for various applications and services. So this is the main components of power system. So we have four here. The first one is generation, followed by transmission, and then distribution, and finally the load. Okay, now let's take a look what is a power generation. A power generation is actually the process of producing electrical energy from various sources, and it has a generator which converts mechanical energy into electrical energy, and it produces real power in megawatt and reactive power MVAR. Okay, and the generating voltage range is between 11 to 20 kV with a frequency of 50 Hz. So this 50 Hz is actually for Malaysia. Okay, and the generating voltage normally step up to 132 kV or 275 kV or 500 kV to reduce the current in the transmission line and to reduce the transmission losses. And it also has a transformer which function is to step up or step down the voltage. And this is the type of generation sources. So here we have a non-renewable energy and also renewable energy. Okay, so non-renewable energy such as coal, natural gas, crude oil, nuclear, and etc. Okay, while for the renewable energy, okay, so here we have solar energy, wind energy, hydro, and biomass, just to name a few. Okay. For the power transmission, it's actually lines or transformers operating at voltage above 100 kV. Okay, and it consists of a transmission tower, like in the figure at the back here, transmission lines, and also substations. Alright, and the transmission lines carry electric energy from the generating site to an electrical substation. And the transmission network of 500 kV, 275 kV, and 132 kV is known as a national grid. This is for Malaysia, right? And it can carry either alternating current AC or direct current DC. Next, for the power distribution, it is actually the final step in the delivery of electricity. Okay, The medium and low voltage power lines normally operated below 100 kV that distribute electricity from substations to industrial, commercial and residential consumers. Alright, so here we have 33 kV, 11 kV, 6.6 kV, 415 volt for a three-phase and 230 volt for a single phase. So again, this is the case for Malaysia, right? And it has a substation which facilitate voltage transformation, switching and control of electricity between different voltage levels, okay, ensuring efficient power flow throughout the transmission and distribution networks. And then for the loads, we have three types here. So here we have residential, commercial and also industrial, okay. So for the residential, for example, such as lighting, radio, TV, washing machine, kitchen appliance and etc. Okay, and usually it increases in the evening around 6 p.m. after we are coming back from schools or from our work, and return to a nominal value around 12 p.m. when we are going to sleep. Okay, and then for the commercial, such as shops, business premises, schools, universities and etc. And the load is fairly constant from 9 a.m. to 9 p.m. And finally, for the industrial, for example, like lighting, motor load, air conditioner, welding furnaces and etc. And it can be divided into small, medium and large categories. And the industrial load curve depends on the number of shifts worked in the industry. Next, we also have a single line diagram here. So what is a single line diagram? So it is actually a simplified graphical representation of an electrical system or network. And it uses standardized symbol, like in the table here, to depict the components of the system and their connections, showing the flow of electrical energy and the relationships between various elements in a clear and concise manner. So this is actually a sample of a single line diagram. Okay, so it is just to simplify the electrical system or network. Okay, next, per unit system. So what is a per unit system? So per unit system is actually a method used in power system analysis to express quantities in a relative and standardized form. Okay, it simplifies calculation and comparison by eliminating the need to work with actual numerical values and units. And these quantities are expressed as a fraction or ratio of their respective base value. So as you can see here, the per unit system value is given by actual value over base value. Okay, and the percentage of impedance is given by the actual impedance over base impedance. Okay, now let's try this example. Given a synchronous generator with a nominal voltage of 15 kV. Calculate the per unit value when the voltage is 13.5 kV. Okay, so you already know that per unit value is given by actual value over base value. Okay, so in this case, actual voltage over base voltage, right? And you already given the actual voltage and also a base voltage. So can you calculate this one? Okay, let's try this one first. And finally, power factor. So what is a power factor? A power factor is actually a measure of the efficiency of an electrical system in converting electrical power into a useful work. Okay, it indicates the ratio of real power or active power or true power to the total power or apparent power consumed by a device or a system. Okay, and the power factor assesses how effectively electrical energy is utilized to perform tasks such as mechanical work or heating rather than being lost as wasteful energy. Okay, now let's try this example. A three-phase motor is rated at 7,500 watts with 5 ohms resistance. Calculate the power losses when the power factor is 0.85 and 0.65. Okay, so the formula for the power is given here, so 3 times VI cos theta. Okay, so let's try first.